Hello and welcome. Today we will covering the basic of message passing interface, that is MPI. It is a programming model and library for parallel computing. So these are the content we are going to cover today. That is, first we cover introduction to MPI, then we cover basic terms in MPI, then how MPI implementation is done, and then we see some sample program. So this is the agenda. First, we do MPI introduction, then we give a brief history of MPI, then we ask one question, basically, what is MPI? So, MPI is also called as the message passing paradigm. So, let's see the history of MPI. So, before the 1990, writing parallel application for different computing architecture was a difficult and tedious task. There was no standard accepted way of doing it, and many different libraries were available, each with its own unique syntax and semantics. During this time, most parallel applications were in the science and research domain. The model most commonly adopted by the libraries, which was the message passing model. In the message passing model, parallel programs are written as a collection of processes that communicate with each other by sending and receiving messages. In the early 1990s, a team of researchers at the University of California started working on a new library for parallel computing that would be based on the message passing model. The goal of this new library was to create a standard programming model and library for parallel computing that would be easy to use and portable to different computing architecture. The library that the researcher developed was called as Message Passing Interface or MPI. MPI was quickly adopted by the scientific community and it remained the most popular programming model and library for parallel computing today. MPI is based on the message passing paradigm. In the message passing paradigm, parallel programs are written as a collection of processes that communicate with each other by sending and receiving messages. MPI provides a number of functions that programmers can use to write parallel programs. It includes functions for sending and receiving messages, synchronizing process, and managing communicators. MPI is a powerful and flexible tool for writing parallel programs. It is used by scientists, engineers all over the world to write parallel programs for a wide variety of applications, including computational fluid dynamics, molecular dynamics, and many more. What is MPI? In MPI, you know as it is the message passing model for parallel computing. So in the message passing model, parallel programs are written as a collection of processes that communicate with each other by sending and receiving messages. All it means is that an application passes messages among processes in order to perform a task. For example, a parallel merge sorting application might sort data locally on each process and then pass the result to neighboring process to merge the sorted list. Almost any parallel application which can be expressed with the message passing model. The message passing model is a simple and elegant way to write parallel programs. It is also a very flexible paradigm and it can be used to write parallel program for a wide variety of applications. The cluster that you will be using to run your MPI program is a distributed memory system. In a distributed memory system, each node has its own processor and memory. The nodes are connected to each other by a network. When you run your MPI program on the master node starts a copy of the program on each node in the cluster. Each node then runs its copy of the program independently. The node can communicate with each other by sending and receiving messages. This is done by using MPI library. Distributed memory systems are very powerful because they allow you to use multiple processors to run your program. This can significantly speed up your program, especially if your program is computationally expensive. So I will give you one example. Imagine that you have a large task to complete, such as painting a house. You could do the task yourself, but it would take a long time. Instead, you could hire a team of painters to help you. Each painter would be assigned a different section of the house to paint. A distributed memory system works in a similar way. Each node in the cluster is like a painter. The nodes work together to complete the task, but each node works independently on its own section of the task. Now we see the basic terms in MPI. Let's see what is distributed memory. A distributed memory system is a parallel computing system in which each node has its own private memory. Computational tasks can only operate on local data, and if remote data are required, the computational task must communicate with one or more remote processor to transfer data. In a distributed memory system, there is typically a processor, a memory, and some form of interconnection that allow programmers on each processor to interact with each other. The interconnect can be organized with point-to-point link or separate hardware which can provide the switching network. The network topology is a key factor in determining how the multiprocessor machine scale. The links between nodes can be implemented using some standard network protocol, for example Ethernet. Distributed memory systems are often used for high performance computing application. HPC applications are typically computationally expensive and require a lot of memory. So distributed memory system allow HPC application to take advantage of multiple processors and a large amount of memory. In the distributed memory system, a program that run on a node is called as a process. When you run is when your program is run, a process is run on each processor in the cluster. These processes communicate to each other using a system of message passing. Message passing is a way for process to exchange data. When a process wants to send data to another process, it creates a message and send it to the other process using the message passing system. The message is a packet of data that is put into an envelope that contains routing information. The routing information tells the message passing system where to send the message. The message passing system copy the data from the memory of the sending process to the memory of the receiving process. This allows process to share data with each other even they are running on different nodes in the cluster. Now we will see what is communicator and group. A communicator in MPI is an object that group collection of processes that are allowed to communicate with each other. When you start an MPI program, all of the processes in the program are automatically grouped into a single communicator called MPI underscore com underscore world. MPI com world is the default communicator and it is used by most MPI functions. However, you can also create a new communicator to group subset or process together. This can be useful for organizing your program and for performing certain type of communication. For example, you might create a separate communicator for each group of processes that is working on a different task. This would allow the processes in each group to communicate with each other without interfering with the communication of the processes in the other group. To create a new communicator, you can use the MPI-COM split function. This function takes a communicator and a color as input, and it returns a new communicator that contains all the processes in original communicator that have the same color. Now, the MPI is a programming model and library for parallel computing. MPI is based on the message passing paradigm, in which parallel programs are written as a collection of processes that communicate with each other by sending and receiving the messages. Two of the classic concepts behind MPI design are the communicator and the send and receive operation. A communicator is an object that group collection of processes that are allowed to communicate with each other. When you start an MPI program, all of the processes in the program are automatically grouped into a single communicator called MPI COM world. MPI COM world is the default communicator and it is used by most MPI functions. However, you can also create new communicator to group subset of process together. This can be useful for organizing your program and for performing certain type of communication. The first is send and receive operation. The send and receive operation is the foundation of communication in MPI. It allows process to send and receive messages to and from each other. To send a message, a process uses the MPI send function. This function takes the message to the destination process and a communicator as input. To receive a message, a process uses the MPI receive function. This function takes the message, the source process and communicator as input. Now we will see what is point-to-point communication. Point-to-point communication in MPI is the most basic type of communication between two processes. In point-to-point communication, a process sends a message to another process by providing the rank of the process and a unique tag to identify the message. The receiver can post a receive for a message within a given tag. To send a message, a process uses the MPI send function. This function takes the message, the destination process, the tag, and a communicator as input. The tag is a unique identifier for the message. To receive a message, a process uses the MPI receive function. This function takes the message, the source process, the tag, and a communicator as input. The process will block until it receives a message with the specified tag from the specific source process. Now see what is collective communication. The collective communication in MPI is a type of communication that involves all of the processes in a communicator. Collective communication is often used to synchronize the execution of processes, to perform global operation on data and to broadcast data to all processes. MPI provide a number of functions for collective communication, which include MPI barrier, MPI bcast, MPI get, MPI scatter, and MPI reduce. Now, the first one is MPI barrier. So it blocks until all processes in the communicator have received the barrier. MPI bcast. It broadcasts a message from one process to all other processes in the communicator. Then came MPI gather. It gathered the data from all processes in the communicator to one process. Then MPI scatter. It scattered the data from one process to all other processes in the communicator. Then came MPI reduce. MPI reduce. It reduced the data from all processes in the communicator to a single value. Now we will understand how parallel execution is done in MPI. So program startup mechanism is that like that. The MPI startup mechanism is responsible for launching the task process of an MPI program and establishing the communication context communicator. The most common way to start an MPI program is to use the MPI run command. MPI run takes the name of the MPI program and the number of process to launch as an input. It then launches the MPI program on the specified number of processor. Once the MPI program is launched, each process is assigned a unique rank. The rank is an integer that identifies the process within the communicator. Now we will see what are the MPI implementation. The MPI is a programming model and library for parallel computing. It is based on the message passing paradigm, in which parallel programs are written as a collection of processes that communicate with each other by sending and receiving messages. MPI is not an IEEE or iOS standard, but it is an industry standard for writing message passing program on HPCs. There are a number of different MPI implementation available, including OpenMPI, MPitch, FTI-MPI, OneAPI, and many others. So MPI is a powerful and flexible tool for writing parallel program. It is used by most of the scientists and engineers all over the world to write parallel program for a wide variety of application. Now we will see how parallel execution in MPI is happen. So the MPI program which I have provided here in this slide, you see this is an example of simple parallel program that use the MPI to communicate between processes. The first two lines of the program include the header file, that is stdi.h and then mpi.h. You know that the stdi.h header file is used for standard input and output, and the mpi.h header file is used for MPI function. The main function is the entry point for all MPI program. It takes two arguments, argc and argv. The argc argument is the number of command line argument and the argv argument is an array of pointer to the command line argument. The first thing the main function does is it initializes the MPI using MPI init function. The MPI init function takes two arguments, argc and argv. Next, the main function get the rank of the current process using the MPI underscore com underscore rank function. The MPI com rank function take two arguments, a MPI communicator and a pointer to an integer variable to store the rank of the current process. The main function then get the total number of processes using the MPI com size function. The MPI com size function take two arguments, a communicator and a pointer to an integer variable to store the total number of processes. Next, the main function print a message to the console that include the rank of the current process and the total number of process. Finally, the main function finalize MPI using MPI finalize function. Now we will see what is communicator. So we also in the previous slide we have discussed about communicator. So here I will explain it briefly. The MPI com size and MPI com rank function are two query functions that can be used to get information about a group of processes in MPI. MPI com size return the total number of processes in the group. This can be useful for writing programs that divide the work among processes or for writing programs that communicate data between processes. MPI com rank return the rank of the current process in the group. This can be useful for writing programs that assign different tasks to different processes or for writing programs that collect data from all processes. Now you will see one diagram here. So here MPI com rank, then inside this function we have given MPI com communicator, then we have given pointer variable. So what it is? The function in this function takes a communicator and a pointer to an integer variable as input. The communicator is a group of processes that communicate with each other. The integer variable is used to store the rank of the current process in the communicator. The rank of a process is a unique integer that identifies the process within the communicator. Processes are numbered here are 0, 1, 2, 3, where n up to we can give n. Here n is the total number of processes in the communicator. Now the MPI comRank function returns the rank of the current process in the communicator. The rank is stored in the integer variable that is passed to the function as an output parameter. Then the MPI comRank function is an important function for writing MPI program. It can be used to write program that assign different tasks to different processes or to write program that collect data from all processes. Now we will see what MPI com size does and how it works. So the function takes a communicator and a pointer to an integer variable as input, like previously. The communicator is a group of processes that can communicate with each other. The integer variable is used to store the total number of processes in the communicator. The MPI comSize function returns the total number of processes in the communicator. The total number of processes is stored in the integer variable that is passed to the function as an output parameter. So here the image which has been shown, it is a communicator with four processes. The processes are numbered here at 0, 1, 2 and 3. Now the MPI com size function take the communicator as input and return the total number of processes in the communicator as output. The output of the MPI com size function is stored in the variable called nproc. And this example, the value of nproc is 4. Now we will see how to compile and run a code. So the command here gcc-o serial.c, it compiled the C source code file serial.c. And it convert into an executable file named as serial. The -o option tells the compiler to name the output file, which is here we have named as a serial. The command /serial run the executable file. So the command now for parallel, the command mpicc-o process.c. It compiled the C source code file process.c into an executable file named as process. The MPICC compiler is a special compiler that is used to compile MPI program. These compilers like GCC you can get from simple GCC version you can load in our HPC like module load GCC or spec load GCC. The MPICC you can get from Open MPI or Intel MPI. From those you can get these name MPICC and GCC. So the command MPI run which I have given -np n /process, it run the executable file process using n process. The MPI run command is used to launch MPI program. The -np option tells the MPI run to use n processes. For example, the following command would compile run and run simple program process.c using 4 processes. Let's take an example. If I take mpicc-o process.c and then for n value here if I take mpi run -np4 /processes. So what will happen? When the mpi run command is executed, it will launch 4 copies of the process executable file. Each copy of the process executable file will be assigned a unique rank. The rank of a process is a unique integer that identifies the process within the communicator. The process program can then use the MPI function to communicate with each other. For example, the process program could use the MPI send function to send a message to another process, or it could use the MPI receive function to receive a message from another process. MPI program can be used to solve a wide variety of problems. For example, MPI program can be used to perform parallel simulation, to process large dataset, and to train other programming model. Now, here I have given for all your code, whether you have written a code in C, C++, or Fortran, how to compile it. So to compile an MPI program for the GCC, we write MPICC. For the C program, we write MPICC-o, then your whatever the after the executable name we have to give. So here I have given the name is executable only, and your program hello world.c. Similarly for C++, you do MPI C++-o, your executable name, then hello world.cpp, your C++ file. Then Fortran compiler, we do MPI Fort-o, and then executable name, then hello world.ftn. So this is the uh, steps which are used for GCC compilation. When if you want to compile with Intel, so what you do is you have to write for the C MPI ICC-o and executable name. Then for the C++, you use MPI ICPC, and for the Fortran, you use MPI iFort. If you want to execute an MPI program after the compilation, then you can do is MPI run -n, then you have to give the number of processes here, and then you have to / your executable name. For example, to execute an MPI program using 4 processes, we would use the following command. that is MPI run -n 4 dot slash executable. So here what it does is it can compile and execute a simple MPI program hello world.c into a 4 processes. So when we see the output of this program, so it will print the message hello world to the console from each of the 4 processes. So at last, the conclusion is for compiling and executing MPI program is a straightforward process. The compiling command listed above can be used to compile and execute your MPI program on the most platform. Now we will see and we will check the difference between if I have written a serial program and if we have written a parallel program. If we compile it with using MPI, how the speed changes. So this is in the demo time, we will see. Here in this presentation, what we have learned is a very simple MPI. So MPI is very vast topic and it requires more than 8 hours to learn it completely. So here I have given the specific and very basic terminology, which will give you a proper understanding what is the difference when we write a parallel program and if we write a serial program and if we run into an MPI on a distributed memory cluster.